All right, lesson 2, measuring the speed of light. So if you haven't already watched this video here, please make sure that you go and do that. In the video, they talk about a whole bunch of different experiments that were done to measure the speed of light. And we're not going to look at those experiments in detail here, except for we will look at the Michelson experiment. You have to know the details of that one. And you also have to know which physics principle is common to all of the experiments in the video. So in all of those experiments, what they're doing is they're measuring the speed of light by taking the distance that the light goes and dividing it by the time it takes. This formula here is the uniform motion formula. And what that means is the light is traveling at a constant speed. And the physics principle for uniform motion, so if you look on the back of your formula sheet, there's a bunch of physics principles listed. It's principle 0. So now we're going to look at the Michelson experiment. So in the Michelson experiment, we have a rotating 8-sided mirror, and this is happening on a mountaintop. And then on another mountaintop that's relatively far away, in this case 30 kilometers, we have a flat mirror. Okay, and we have a light source, so this could be a laser or just something that gives off light. The light comes in, it hits the rotating mirror, goes to the flat mirror, comes back, and then goes into the observer's eye. And we'll talk more about this experiment in a second. All right, so we have the setup here. So this is supposed to be the mountain that's far away, and when I turn the light on, that's going to represent light coming from that mountain, okay? And then it's hitting this 8-sided mirror right here. Now, since I don't actually own an 8-sided mirror, I am using a flat mirror, and I'm just putting it against one side there to show what would happen if I had an 8-sided mirror. And then over here, this is the observer. And so if we turn on the light, as long as everything is lined up perfectly, then what happens is the light comes from the mountain, it hits the 8-sided mirror, and then it travels and it hits the observer's eye. Now, you don't ever want to actually shine a laser in your eye, by the way. I'm just using an eye here to help me talk about what's happening. But what I'd like you to notice is that if this 8-sided mirror is rotated even just a little bit, then the light doesn't go into the person's eye. So if I shift it just a tiny bit one way, maybe a little bit more, now the light is not actually going into the person's eye. Okay, if I shift it slightly the other way, again, the light actually isn't going into the person's eye. And we won't worry about this too much, but how your eye actually works is if light doesn't actually hit the retina at the back of your eye, you can't see it. All right, so we have here the setup of the Michelson experiment. So I'll just explain. Down here, okay, we have our light source. So our light is coming in, it's hitting the 8-sided mirror, it's going across to this flat mirror, coming back, hitting the 8-sided mirror again, and then going into the observer's eye. Now, remember I was saying a minute ago that the 8-sided mirror has to be lined up perfectly to send the light into the person's eye. So what we're going to say is the edge of the mirror has to be lined up with this black line in order to actually send the light to the person's eye. Okay? When they did this experiment, they knew that light traveled at a constant speed. So they knew that the amount of time for the light to travel this path here was always the same amount of time. And they also knew, okay, that if they could find the distance for this path and the time that it took, just by doing distance divided by time, you could figure out what the speed of light was. The problem is that light travels so fast that trying to go and measure time for that to happen is actually really difficult. You can't just use a regular timer. So in the experiment, they actually used their 8-sided mirror and they rotated it and used that as a timer of sorts. So I'm going to try to explain how that actually works. So what I've done is I actually just have an animation here that's supposed to represent the light going from the 8-sided mirror to the flat mirror and back. And because light travels at a constant speed, every time I play that animation, it's going to take the same amount of time for that path to be drawn out. Okay, so this time I'm going to play that again. And this time when I play it, I'm going to rotate the 8-sided mirror while it's playing. So something like that. Okay, and what I tried to do is I tried to make it so that at the moment the light came back and got to right here, at that exact moment, the 8-sided mirror had completed 1/8 of a turn. So because it made exactly 1/8 of a turn, that means that it, so it started like this and it ended like that. If it had been a little bit more than 1/8, it would have ended like this, and the edge of the mirror wouldn't be lined up with this black line that I drew. If it had made a little bit less than 1/8 of a turn, it would be like that, and again, they wouldn't be lined up. Okay, but because it made exactly 1/8, it was lined up perfectly, and then when the light came back, it would get sent into the observer's eye. So now, suppose you're doing this experiment, and you know how much time it takes for the mirror to make one full turn. The time for one full turn would be called the period. We know that it made 1/8 of a turn. So therefore the time for the light to go there and back would just be 1/8 of the period. Okay, now let's do that one more time. And this time I'm going to try to spin the mirror just a little bit faster. So I'll start my animation. And I'm gonna spin it, and there. Okay, and this time what I tried to do is I tried to actually turn this 2/8 of a turn. So again, it started like this, and then I turned it 1/2/8. But again, because I turned it exactly 2/8, notice that this side of the mirror is lined up with this black line, and so everything's lined up perfectly to again send the light into the observer's eye. Okay, so if you're doing this experiment, what you do is you play around with the rate of rotation of this, and you figure out what rate the 8-sided mirror has to be rotating at to send the light into the person's eye. And if it's rotating at the wrong rate, then every time the light comes back, the mirror is not lined up properly and the observer doesn't see anything. But if it's rotating at the exact perfect rate, then when the light comes back, everything lines up and it works. And so then you can figure out, based on how this thing is rotating, you can figure out how much time it took, and then you can calculate the speed of light. So now that we've looked at that experiment, we're going to try to derive a formula that we can use when we're doing Michelson experiment questions. So we're going to start with V equals D over T. And let's see, up here on this side of the screen, I will make a list of variables. So we're just going to go back for a second. 30 kilometers, that's the distance one way from the rotating mirror to the flat mirror. We're going to call that capital D, just to distinguish it from lowercase d here. So capital D, this is going to be the one-way distance between mirrors. Okay, so because the light goes from one mirror to the other and then back, up here, so it's going to be 2 times capital D all over T. Okay, now we're going to talk about T. So remember I had said a minute ago that to calculate the time, if it was an 8-sided mirror, you could do 1/8 times the period. So remember, capital T, that's period, and capital T is a really specific amount of time. Period is the amount of time for the mirror to make one complete circle. So because it's only making 1/8 of a turn, that's why we're doing 1/8 times that. Now, we're going to make this a bit more general though. So a lot of times it's not going to be an 8-sided mirror. It could be a 10-sided mirror or some other number of sides. So to make this work for any situation, we're going to replace 8 with S, okay, where S is the number of sides on the rotating mirror. Okay, now the other thing is in these questions, they'll often give you the frequency instead of the period. So you might remember the relationship between period and frequency looks like that. So period is 1 over the frequency. And so if we take this formula up here and we just rewrite it, we're going to have 1 over S, and then instead of writing period, we're going to write 1 over the frequency. Okay, now one other thing we have to do to make this a little bit more general is, remember I said that when you have a rotating mirror, you can rotate it by 1/8 or 2/8 or 3/8 even. Any of those are allowed, but what would not be allowed would be rotating it by 1.5 out of 8 or 2.7 out of 8. You always have to be rotating it by a whole number. So we're gonna make one more change here. Up here, right, instead of writing 1/8, I could have written 2/8, okay, or I could have written 3/8 or whatever. And so we're going to change this to N, okay, where N is the number of sides the mirror shifts by. And so that's going to actually change this. So instead of being 1 over S, we're going to write N over S. Okay, so let's put all of this together. So now, okay, we have V equals 2D over T. So I'm just going to rewrite this. Okay, and where we see T, we can replace it with all of this. We rewrite this a little bit nicer. So N times 1 is N, and S times F is just SF. So this is going to be 2D over N over SF. And so simplifying that, we're going to have 2D times SF over N. Okay, so for the final thing here, rewriting this, the speed of light, V, is 2D SF over N. So there's a couple variables in there that I haven't written out yet. Let's just do that quickly now. So V is the speed of light. And then F is the frequency of the rotating mirror. And just add units in here. So capital D should be in meters. S and N do not have units because they're just number of sides or number of sides that it's shifting by. Speed is going to be meters per second. And then frequency is going to be hertz, which is the same thing as 1 over a second. So let's do an example to see how to actually use that equation. So in a Michelson-like experiment, a rotating 8-sided mirror, so S is 8, was placed 50 kilometers from a reflecting mirror. So the distance between the mirrors, which we're calling capital D, is 50 kilometers. Make sure to convert that to meters though, so 50,000 meters. The observer found that in order to return the light ray, the mirror had to rotate at 375 hertz. What is the speed of light? You can call that V, or you can call it C. Either way is good. And so what we're going to do is we're going to take our equation that we came up with on the last slide, which by the way is not on the formula sheet. You have to know how to derive it or memorize it. And we will plug our numbers in here. So 2 times 50,000 meters times 8 sides times 375 hertz which I'm going to write as 375 1/seconds, all over n. Now, if the question doesn't say how many sides the mirror shifts by, so in other words, you don't know if it's turning by 1/8 or by 2/8 or 3/8 in the time that the light goes there and back, you're going to just assume in that case that n is equal to 1 if it doesn't specify. So we'll say n is 1 here. And I've gone ahead and I've actually calculated that already. And that gave me 3 times 10 to the 8. And you can see here the units you're going to get are meters per second. And there we go. So when you're doing Michelson questions, you're usually going to get an answer that's close to 3 times 10 to the 8. It could be a little bigger or a little smaller. If it's not exactly 3 times 10 to the 8, that's nothing to panic about. Okay, for example 2, you'll need to add this distance into your notes booklet. So in a Michelson type experiment, the path followed by a beam of light when a 10-sided mirror is at rest is shown. The detector indicates a maximum signal. Okay, so down here we have a light detector. This is behaving like the observer's eye. And what they're saying here is when the 10-sided mirror is at rest, the light is following this path here. Okay, and it's going into the light detector. The reason it's a maximum signal is that all of the light that originally comes right here, all of that light is eventually making it into the light detector. Now it says, as the 10-sided mirror begins to rotate, the beam of light no longer follows this path. So the idea is they're now starting to rotate the mirror, but the mirror is probably rotating too slowly. And so when the light gets back to right here, some of it is getting directed here and some of it's getting directed the other way, but not all of it is going into the light detector. So once in a while, if that mirror happens to line up the right way, the light detector might see a flash of light, but it's not going to see light continuously because things aren't lined up properly. So that's why we're seeing a decreased signal. Now, as we increase the frequency of rotation for this rotating mirror, eventually we're going to hit the right frequency to again see a proper signal. So that's why it's saying once the 10-sided mirror is rotating, the frequency for which the light detector will first indicate a maximum signal is. So we know that when we have that mirror rotating so that it's making 1/10 of a rotation in the time that it takes the light to do this, that's when we're going to start to see a maximum signal again. We would also see a maximum signal again if we continued to increase the frequency and then had this rotating mirror make 2/10 of a rotation in the same amount of time. But they're telling us that they only want us to actually do the case where it's making 1/10 of a rotation, because it's saying we want to know the first time that we see that maximum signal. So because it says the word first here, what that's telling us is to use an n value of 1. Okay? If it asked for the second time, then you would use n equals 2. We'll come back to that in a second. So let's keep going here. So writing down our other variables. So S is going to be 10 because it's a 10-sided mirror. Capital D here was 40 kilometers or 40,000 meters. We're looking for the frequency. Now, if you're looking for the frequency, you're going to have to assume that the speed is just the speed of light, which is on your formula sheet. So we'll assume that it's 3 times 10 to the 8. Okay, so we're going to have V equals 2dsf over n. And we're looking for f, so this is going to be Vn over 2ds. Okay, so 3 times 10 to the 8 times n is 1. 2 times 40,000 times 10. Okay, and I calculated that already. And I got 375, and this is a frequency, so it's going to be hertz. Okay, or because this is a numerical response question in your booklet, this is going to be 3.75 times 10 to the 2 hertz. So you would bubble in, just out of room, 3752. Okay, and then the physics principle used to solve this question is just principle 0, like we discussed earlier in the notes. Okay, I just want to go back to this for a second. If the question asks you for the lowest possible frequency that you can use and still see a maximum signal, then that means n is 1. If they ask you for the second lowest frequency, then that means n is 2. If they ask you for the third lowest, then that means n is 3, and so on. So hopefully you're seeing the pattern there.